Okay, first Sunday of the month, 7 o'clock, time for chai and wine. We have a very intriguing topic today. As you can see, it's about coloring maps and keeping secrets. And those of you who are here, you recognize something which is probably you've not thought of it as being related to coloring maps. For the online audience, I'm just going to turn it so that maybe you can see that they have a yeah, there's a Sudoku board there. It's a pleasure to introduce Ramprasad. Ramprasad, I don't know about your background and something, so you please introduce yourself before you start.
Okay.
And once you are ready, you can share screen and then we will start off.
Yeah.
So you can introduce yourself. Yeah, and let me know when you need me to distribute things.
Actually, we can distribute them now.
Yeah, so online audience, we are going to do some map coloring over here. Hopefully, Ramprasad will also display on a screen and you can try to follow online. But if you are here, you could actually try these activities.
So they will also be able to do it from where they are
You
sitting.
can do it from wherever you are. You can click and do things and figure it out. But for those who are here, we can hand out some of these papers for you to try coloring maps. Yeah, why don't you introduce yourself? You can share screen if you want now.
Okay.
And,
just a second. Let me share screen.
we get the papers. Background. Yeah. So we just
Oh, so here I need to do. Is there something that I need to do here?
You got blur background on. Blur my background. Just remove blur my background.
Acha. Okay.
On your video options here. Just remove blur my background. Exactly.
Ah, perfect. Okay.
So he was blurring.
Sorry, my bad.
You need to start the login.
Yeah,
I need to start the login.
Thank you. So we can distribute the papers if we want. So while the papers are being distributed, let me introduce myself. My name is Ramprasad Saptarishi. Okay, we'll wait for a little bit.
Yeah. Should we give you folks want colored pencils? So we
Okay.
4 colored pencils.
Yeah. I mean, you can pick up the fewer pencils you use, the better. But I mean, pick up as many as you feel it may be necessary. We just leave the box there, and maybe anyone who wants can just pick up something.
You want to So we have pens, we have color pencils. Maybe what you can do is you can so give people 4 or 5 colors. They should not need more than that.
Yeah.
That's a good point.
Okay. So in the meantime, let me then introduce myself. So my name is Ramprasad Saptarishi. So I work at the Tata Institute of Fundamental Research. I am one of the faculty at the School of Technology and Computer Science. So what I want to talk about today, I mean, like, since Holi is around the corner, like, this is a talk that's going to be based on colors and so on. But there's a larger message that I want to make, which is that a lot of what happens in research is really just spending more time trying to solve puzzles. So the hope of today's talk is to sort of start with something that I presume some of us have done when we were young and so on, and slowly get you to what is being done in the current world of internet and try to somehow connect them together. I can completely understand some of you wondering what is the connection between coloring maps and Sudoku puzzles, etc. But through the talk, we'll have a better idea of things. Okay, so let me start. So I'm going to basically say, so this is what maps are going to be. Okay, so this iPad is not working for that. So we're all familiar with maps of this form. Okay, and the rough idea is that, you know, you're always going to assume that all of these maps are going to be drawn on paper. Somebody gives you printouts like you have been given, and there are regions that are marked off. Maybe these regions are states, maybe these regions are countries, districts, whatever be it. Okay. And your goal is to color them in such a way that, two regions that are touching each other or that are neighboring each other get distinct colors. So that way you can tell apart one state from another or something. Okay. And we would like to use as few colors as possible because we need to somehow bring in something competitive here. So we can sort of say, what is the smallest number of colors we can use? Okay, so that's going to be the game that we are trying to play. Okay, so let me talk a little bit about some details which may confuse a few people, which is that when two regions touch at just one point, I'm not going to think of them as touching each other. They must touch with respect to a border. Like for instance, if you have a region that looks like a windmill or something, then each region is basically only touching two neighboring regions. I'm not going to say they're all touching each other because they touch at the center. Okay, so if I were to ask you how many colors do you need to color this, how many colors would you end up needing? You will basically color it red, blue, red, blue, red, blue, and so on. And you can see that you can just color it using two colors. Fantastic. The other thing we are going to assume is that all regions are going to be made up of one piece. So there are no broken up chunks which are at various places. Like while preparing the talk, I learned a lot of things about India. So for example, the Union Territory of Pondicherry is actually split into 4 parts. There are 2 pieces that are touching Tamil Nadu, one piece touching Kerala, and 1 piece touching Andhra Pradesh. Okay, so those sort of situations we are going to assume don't happen. And I also learned that, so for example, you can't say the 2 blue regions are actually touching each other because there is some bridge that is going from this blue region to that blue region. No, such things are not allowed. And I also learned that until 2015, there used to be this place called Dahala Kagrabari. I mean, the place is still there, but now is a part of Bangladesh. And this was a small part of India, which was within Bangladesh, which was within a part of India that's within Bangladesh. So these were like the 3rd level enclaves that were present or something. We're going to assume these sort of complications we don't have. We are going to deal with very simple looking maps. Okay, good. So as always, we're going to start with some examples. You have some pieces of paper. We're going to try them and we're going to see how many colors we need and hopefully we learn something out of it. So we'll start with some simple examples. The first one is not on your piece of paper. So here is an example. How many colors do you need for this? Okay. Oh, thank you. Yeah. Okay. How many colors do we need for this? Okay. So how many people can do it with 1? Okay. What do you want to color? Everything is going to be colored red. So then you're using 2 colors. Yeah. Okay. Red and white or whatever. Right. So basically the simplest form of coloring it is like you just think of this as a chessboard and just color it like as if it's a chessboard. Okay. And just to remind you, even though these 2 regions seem to be meeting at this point, that doesn't count. I mean, it's okay for both the regions to get the same color. So far, so good. Okay. Now let's do the next warm up. This is the map of what? Australia. Good. Those of you who are joining us online, you could just point your phone camera at this QR code. It will take you to a certain web page where you can play with it. Like actually, I would actually like some members of the audience to actually try it out here. So I'm going to open up the same thing, and can we have someone? So who would like to come try? Okay, please come. Yeah. Yeah, you can come on. You can. Okay. So just click any of the regions that are there. The color will change, and try to color them using as many colors. Okay. So that is colored red. So you can click it once more, and then it will change the color. Okay, good. Okay. We have used 3 colors so far. That could be 4. Maybe this is 5. Right now, the 2 greens are touching each other. So we can change that to blue. Fantastic. Okay. So right now, I'm going to also color Tasmania with red. And there is a small, I think this is Victoria. Okay, that's too small for me to touch it and color it. But as we can see, here is an example of a map where we managed to color it using how many colors? 1, 2, and 3 colors. Okay. Okay, good. So yeah. So the QR code, if someone just scans the QR code, it will show them to take them to the website. Otherwise, the link is present below. Yeah, 3 capital E capital J. 3 capital E capital J. E small h small c capital U small z. Okay, good. So that is warm up number 2. So now let's try to do something a little trickier. You have printouts with you of this map. Okay, if you want, you can just use the app to, you can scan the QR code and click and do it yourself, or you may want to color it using this. Okay, I will also sort of say that for people who are joining online, to be fair with people who are actually going to be coloring on pieces of paper, notice that once a person colors some region using a certain color, you can't change it after that, because we don't know how to erase sketch pens. So those of you who are doing it online, you should sort of take this as a rule that once you decide to color a region with a certain color, you're not allowed to change it. To be fair, but we can just think of it as a game. Okay, I'll let people try it out for a little bit.
So first you have to decide what you're going to put and then start coloring.
Yeah. So does someone want to try it out on the machine? Or maybe I'll just open the page, someone can just scream out what colors you want, and I will set the colors accordingly. Okay. So any suggestions? What should I color first? Okay. So I'm going to put it red now. Okay. Green. Okay. So this can't be red or green. So this has to be red or blue. So it has to be a different color.
Like blue. Oh, why can't that be blue?
Okay, we could put this as blue. Okay. Okay, we use a 4th color. Fine. Now what do we put here? Green. Here. Okay, so let's put red and see. Here we'll put light blue because we are forced to. Here red, and here blue. And now the outer part also needs to be colored. Okay, so we need to use a 5th color. Okay. So can someone? Okay, I'm curious. So do people want more time to color it on their pieces of paper? Okay, in the meantime, you can just write 1, 2, 3 if you are too lazy to color them. You can just put numbers 1, 2, and 3 if you want. Or you could use white as a color to.
If anybody came late and wants colors, we have lots of color pencils.
Yeah.
So you can share with people around.
So in the meantime, I was calling this the football graph or the football map. So does this remind you of the ball that is there on top in some sense? So in some sense, there is a connection with the ball there on top. If you want, you can think about why that is the case. But yeah. Okay. So now that we've had some experience with respect to coloring maps, etc., there are a few questions that immediately come to our head. Okay. So I'll just wait for people to maybe spend more time coloring it. Yeah. So you're supposed to put the color for this outer, the circle that's enclosing the whole thing. That's like the world ocean in the football map. Yeah. Yeah. Okay. Yeah, then for example, each sort of sliver could have been a different color, but now you are forced to. Okay, so were there people who could do this with 4 colors? Okay, great. Were there people who could do it with 5? Were there people who needed 6? Okay, great. So as you can imagine, I mean, like this immediately, leads us to a bunch of questions, which is how many colors do we need? If I give you a map and I ask you, I want you to color it such that neighboring regions get different colors, how many colors do we end up needing? Okay. So in some cases, we seem to be able to do it with 4, but is it the case that we can always do? The second question could be, okay, maybe it can be colored using 4, but can we do that quickly? So there's a question of efficiency. So is this something that I can do quickly? And some of you, I'm sure, are wondering, what the hell is it about Sudokus and so on? What has that got to do with Sudokus here? Okay, we'll get to that part later. So now let's ask ourselves, how do we color maps in general? Okay, we are going to try this example, which is this big Maharashtra district map. Okay, but let's ask ourselves, what did we really do? We basically picked a region that was not colored so far. Okay, and we gave it a color that was different from its neighbors that have been colored at this point. So at any point, your region maybe had a bunch of neighbors. Maybe one neighbor had red, the other neighbor had blue. So you decided to give it, okay, I'll give it green. Okay, and in some sense, it feels like, what else can you do? Okay, so we're going to play with the Maharashtra map. So does someone want to come here as a volunteer to try it out? Yeah, please come. Okay, so you can, once again, you can click on any region and that will color that particular region.
Someone wants to scan the QR code here.
Oh, sorry. Just give me 1 second. I'll just show the QR code to people. So those of you who want to do this on your own phones, or maybe people who are doing this online, you can just scan the QR code and that will open the same page. Can I have your name? Sanvi is also going to be demonstrating here. You could also do that on your own if you wish. Yeah.
So Ramanagar is easier when like some region comes up like Andhra Pradesh and Telangana. So you already know all the neighboring colors. You just find one more color.
Yeah, we'll see. So the thing is, I don't want to keep on adding one more color every time a new region comes up. I would like to use as few colors as possible. So we'll take this example because this is a large enough map that we will see, can we do it with 4? Can we do it with 5? Do we need 6? And so can we go on to the page? I mean, I hope people who want to scan have scanned. Okay, cool. So yeah, you can go ahead now. Yeah. Okay. So I think there is a small, I think Bhandara and yeah, I think these two reds are touching each other a little bit. You can change the color to something else. Okay, green. Yeah.
One point where I don't know if are they considered neighbors or not.
Oh, which one?
And
So this one. So here. Yeah, no, these two are touching each other. I mean, there's a border. So they are supposed to get 2 different colors. Yeah. By the way, I must also say I cheated a little bit in this map. Mumbai is really made up of two districts. There is Mumbai city and Mumbai suburban, but Mumbai city was so small that I couldn't quite click it properly. So I just decided to put it as one district. Yeah.
Yeah, Mumbai plus Thane.
No, that's just yeah. Thane is the red one. Yeah. Mumbai is currently colored pink. It's a darker. I mean, like it's. Okay, great. Okay, so fantastic. So we now have a coloring of the districts of Mumbai. How many colors have we used so far? Red, blue, green, light blue, pink. So we've used 5 colors so far. Is that right? Okay, good. So now, okay, let's go back and among the people who probably did colorings on their own, was there anybody who could do it with less than 5? Did someone manage to do it with 4? Okay. Did someone manage to do it with 3? If someone managed to do it with 3, they have made a mistake. So this can't be colored in 3. We'll see. Okay. Okay. So now we can ask ourselves, what can really go wrong if we try doing this thing? We pick a region that hasn't been colored. We find all its neighbors that we have assigned colors. Give it a different color. What else can we do? Okay. So what can happen is something like this. Okay. So you colored all other regions. Maybe this region got yellow, this got red, this got green, etc., etc. And now you are forced to color this region, and you realize that you have run out of sketch pens. You know, all the colors have been used up for all the neighboring regions. Now you're like, no, I need one more color. Okay. So that's the whoops that happens when you start trying to color, and then you suddenly realize that you don't have enough colors with you to color them. So the important thing that I want to take away from here is that the order in which you color the districts or regions matters a lot. Okay, so let's do a pop quiz. Here are 2 districts. One is this district called Nandurbar, and the other is the district of Ahmednagar. Okay, and which should you color first? Okay, so some of you feel we should color Ahmednagar first. Some of you feel we should color Nandurbar first. So just want to get a vote. How many people want to color Nandurbar first? Okay, there's a 6-7 people who seem to want it. And how many people think we should color Ahmednagar first? Okay, how many people think I am asking the wrong question? Okay, good. In fact, I am asking the wrong question. In fact, in order when it comes to coloring maps, the question to ask is not what you should color first, but rather what you should color last. Okay, so if I were to now ask you, which of these 2 districts should you color last? And why is that? Excellent. So the point is, even if I manage to color the rest of the map in any way that I want, when I come to coloring Nandurbar, I've only used up 1 color. So I have a lot of options at that point. But on the other hand, if I had colored the rest of the map besides Ahmednagar, I might end up in that whoops sort of situation, where all the neighboring districts happen to get different colors, and now I don't have enough options. So the rule about coloring maps is that the lowest degree should go last. By lowest degree, I mean pick up a district that has the fewest neighbors, color that last. Okay, and now this immediately, so turns out that in any such map, yeah, please go ahead. Yeah, but the point is, it's also so the question that was asked was, I was saying that the lowest degree district should go last. The question was, is the highest degree district going first? The answer is a little bit of yes and no. So there are some high degree districts here. Like for example, Ahmednagar is a high degree district, Bid is a high degree district, Pune is a high degree district, etc. But I don't want to color all 3 of them one after another. So it is true that I will be coloring the high degree districts first, but there also the order is going to matter. What I'm more sure of is what I'm going to do last. And we will see a demonstration of that. Okay. Now turns out in any such map, okay, there is always going to be one region with 5 or fewer neighbors. I'm not going to show why this is the case, but turns out it is the case. And this immediately tells us that, we don't need more than 6 colors. Why is that? We'll find that one region that had only 5 or fewer neighbors. Suppose we remove that from the map, color the rest of the map. I can always put it back. At most 5 colors have been used, so I have a 6th color left. So I'll color it using that color. Okay, this may be we're going to do a demonstration of this, but this is what is called the 6-color theorem, which is that 6 colors are enough to color any map. So we're going to do that for the Maharashtra district. We already saw a demonstration, but we will do this using this method. Yeah, please go ahead.
The fact that there's at least one region where or there are maximum 5 neighbors. That's not the case, right?
No. Like, for example, Ahmednagar, I think, has something like 7 or 8 neighbors, if I remember right. So there could be some of these districts which are connected a lot. But all I'm saying is that there will be something along the edges which probably have very few neighbors. And so I can always remove them, color the rest of the map, and then put back that and color it. Okay. So what we are going to do is we're going to see this in action. For those of you who are going to be joining online, if you scroll down, you will see a button that says watch this. If you click on the button, you get this thing called peel and color. Okay. So what we are going to do is we're going to slowly peel off one region at a time, so that the map then becomes empty, and then put back one region at a time, and then keep coloring them as we put things back. Okay. So I'm going to start the peel mode. What should I peel? Can you give me some district that has very few neighbors? So which one should I take this? Okay. So Sindhudurg I've removed. Let's again, Bombay is adjacent to just one other thing. You can remove that. Maybe Nandurbar. How many neighbors does this have? This has just 2. So let me remove that. This also has only 2. I'm going to remove that. Now which one maybe let's go to the other end. Okay, this has, I don't know if it's touching, but anyway, even if it's touching, it has at most 3. So we'll remove that. We'll remove this. Then this. Anybody else? Where would you like to go? Does someone want to try? Okay, yeah. Which one do you want to remove? Which one? Yeah, we'll remove all of them and then slowly add one at a time and color. Which one? So that's adjacent to 3 of them. We remove that. Shall we remove this one now? Yeah, you can click on that. Yeah. And now how many? 1, 2, 3. Let's remove that. Okay. And which else? That is also adjacent to 3. 3. That is adjacent to just 2. Fantastic. Then we remove that. We remove that. Now which one? So this one is adjacent to just, okay, we remove that. Okay. And now this one is adjacent to just 2 of them. Okay. Now that's adjacent to 3 right now. Okay, that's fine. This is also adjacent to 3. Yeah, we can remove that. That is adjacent to 1, 2, 3 of them. Okay, so that is adjacent to 2. That's adjacent to 3. That's adjacent to just 2. And then we remove this, and then that's adjacent to 2. Okay. Now we can remove this part. 2. Okay. Now the map is empty. Now I ask you, can you color this map using 6 colors? Well, of course you can. Okay. So now what we are going to do is we're going to put back one region at a time. Now I ask you, can you color this map using 6 colors? Yes, I can. Okay. Okay. Now you can sit if you want. Okay. So now let's put one more region. Can I color this map? Well, okay. Can I color this? Okay. What color should I give here? Blue. Okay. This can be red. it can't be red, it can't be blue, it can't be this, so it has to be light blue. This can be red. This can be green. This is going to be blue. Again, blue. This can even be red. This has to be light blue. And this can be dark blue.
So are you going in the order?
Yeah, I am basically doing in the reverse order in which we peeled off. And that's why the map is sort of growing from the inside to the outside in some sense. Yeah. So, and in fact, when you color it using your paper, almost nobody does it from the center. Like you would often think of coloring it either from this side or from this side or from the top or the bottom. But somehow it feels like the better thing to do is actually do it from the, like whatever is the harder ones, you color those first. Yes. Yeah. I mean, the football thing, everything in some sense is the same, but yeah. Actually, the football, every piece is adjacent to 5 other pieces. Okay, so let's, oh, this could have been red, right? Okay.
Now, as you're coloring, you're also making sure that you're not going beyond your shape.
Yeah, so if you notice the way every time we removed a region, it was adjacent to only 3 regions or fewer. So you will never end up needing the like anything beyond the 4th color now. Because at any point you have 3 colors that are out of commission. You can't use any of those 3. You will always have a 4th color that you could use. Okay, so this is going to be light blue. This dark blue. This is red. And this is blue. This is red. So this can be green, right? Yeah. And this, maybe it has to be light blue. I don't know if it's touching. This is green. This is green. This can be red. Then there's Mumbai, which will make it red, green, and that's it. And now we have colored the district of Maharashtra using 4 colors.
So one second. So the top right one
Uh-huh.
would have been either like or.
Yeah, I think these 2 regions don't really touch each other, so it could be dark blue if you want. But yeah.
So now can have right.
Yeah. Okay, great. So this basically is a way in which we can color maps a little more efficiently. I mean, we can be a little bit clever about how the order in which we are coloring maps, which is we keep removing regions that have very few neighbors and then start coloring in the reverse order. Okay, good. So now this is the theorem that was known for a very, very long time, which is that 6 colors are enough for any map. And obviously we should ask ourselves, can we do better? Okay. And so so far all examples we saw seem to require 4 colors, but for the moment we are able to show only 6. So let's first try to see when do we have to end up using the 6th color. Okay. So we are forced to use the 6th color if we have already found we are in a situation where all 5 neighbors somehow involved all the other 5 colors. Then unfortunately I'm stuck. So for example, this is an example where notice every single piece is adjacent to 5 other pieces. Like this is adjacent to this, and the outer. And the central thing is adjacent to 5 other pieces, etc. So maybe if you try to color this, you will somehow end up in a situation where you have 5 of the neighbors, all of them ended up getting different colors. So you are forced to use the 6th color in the middle. So there's a really nice trick, which is if I can somehow ensure that 2 of those neighbors actually got the same color, then I will have if I have a 5 sketch pens, 1 color will still be left. I can use the 5th color. So the way to force this is to somehow remove 2 of the borders. Let's just imagine that these 3 pieces are now one big piece. Okay, now this is our new map. Let's try to color this map now. Okay, maybe someone gave you a way of coloring this map. Now you put back the borders. Now you are in a situation where this piece is adjacent to 5 other pieces, but 2 of your neighbors now use the same color. So you have one free color left with you, which you can then use to color the center. Okay. So this is what is called the 5-color theorem. Okay. So we started off with not knowing how many colors we could use, and then we ended up with, okay, maybe we showed that how we can use with 6, and now we have gone to 5. Some of you have already heard this thing, which is that 4 colors are actually enough for any map. And this is the celebrated 4-color theorem. Okay. I'm not going to be able to show that in this talk, and I will tell you why. But there's a really beautiful history behind the 4-color theorem. So this question of, are 4 colors enough to color any map was actually conjectured by a person called Guthrie, who was a student of De Morgan. You may have heard of this name. And apparently he was looking at the map of UK and London and somehow noticed that all the maps that he could find, somehow 4 colors appeared to be enough. So he asked his advisor, is this actually the case? And then De Morgan wrote a letter to other people saying, by the way, one of my students seemed to ask this question. I don't know if this is true, but every map I'm able to try seems to have this property. So Kemp in 1879 actually gave a proof of this, showed that 4 colors are enough. And shortly after that, Tate actually gave a different proof of it, saying that 4 colors are enough. But turned out both of these proofs were wrong. Okay. But the surprising thing is it took 11 years for people to realize that the proof had a mistake. Okay. It was a very, very tricky counterexample to somehow show that, the argument used by Kemp was wrong. Okay. And it took 11 years. And it was eventually, Hewood, who was one of the people who found the wrong proof of Kemp, actually showed that, okay, Kemp's proof for 4 colors is actually there is a mistake, but you can salvage something out of it and show that the 5-color theorem is true. In the sense that, okay, 4 colors was the argument that was had was not correct, but nevertheless, the same argument allows someone to see that 5 colors is enough. Okay. And if there is a really beautiful video of Timothy Sun on YouTube, which speaks about the 5-color theorem. And it's a fantastic video. I would highly recommend people check it out if they haven't seen it. And then finally, in 1976, that's not a typo. These are all results that happened in the 1800s. It took 1976 to finally show that the 4-color theorem was true. And this was one of the first results that actually used computers to verify their thing. So in fact, the way the proof worked was the following. If there is a map that cannot be colored using 4 colors, one of these 1834 maps cannot be colored using 4 colors. And these 1834 maps was fed to a computer and said, can you please confirm that these are all colorable? So that's what happened. So it's a really complicated proof. And to the point where when this proof came out, it was a philosophical question to many people, because to them it was like, hey, this is not fair. You can't ask a computer to solve something that you are supposed to solve by hand. Okay, so does this actually count as a proof? Does this count as a theorem being proved or not? So this was something that was debated a lot then, but over time it has been accepted that this is very much a legitimate thing. Yeah, it happens to have 1834 cases. What can we do?
There were computers in 1976.
Yeah, so apparently it took like months to do this, but then probably these 1834, if we run it on our cell phones, we can probably get it in seconds. But at that point, this took a lot of effort to do this. Subsequently, there have been results which have improved this 1800 cases to 600 cases, but it still uses a computer to verify. Okay, so that was for the 4-color theorem. Yeah, I don't know. Right now to me it feels like, so the question is, what is wrong in using a computer to prove a certain result? At the moment, to me, this seems perfectly fine. Why should I not use a computer to check some cases, etc.? Yeah, there was a question.
Using computer, you can only inductively prove something, not deductively. Right?
So, for example, these 1008. So the question was, a computer can only be used to inductively prove something or something. But here, this was 1800 specific maps and there was a proof that said if all of these maps can be colored using 4 colors, then every map can be colored using 4 colors. Now somebody has to verify.
Different than.
Yeah, that was different, but somebody has to verify that these 1834 maps can all be colored using 4 colors. And
that there might be 1835 map that might not be.
no, so the Appel and Hacken's proof, they basically said it was something like this. If you look at what we did, we said that there will always be a region that has 5 or fewer neighbors. Suppose let's imagine that I had a graph where there was one region that had 3 or fewer neighbors. If this graph cannot be 4 colored, even removing this region, the graph should not be 4 colored, right? So these were sort of cases of that type. Okay, and somebody had to verify this. You can say, okay, let's spend 5 years sitting and coloring all of them and figuring out which one is there. They basically said, why are we wasting time? Why don't we ask a computer to do this? But somehow at that point, this was sort of frowned upon, saying that no. I mean, like a mathematical proof has to be mathematical. You can't sort of say that no computer has verified something and so on. But over time, people have come to terms with it because computers are now part of our day-to-day lives, etc. But it was a major paradigm shift. Yes, please.
Is there no formal proof for this? Or is there a formal proof, but you have verified that?
So there is a formal proof that says that if the 4-color theorem is wrong, it is wrong on one of these 834 cases. And for each of these 834 cases, a computer will tell you that I can color that map using 4 colors. Now, in my opinion, that is a formal proof. But to a person, I mean, maybe some people say that no, a proof has to be written on paper by somebody. You can't ask a computer to do your job for you or something. But in my opinion, this is a perfectly legitimate proof. And over time, it has become accepted in the community at large. Yeah, please.
Particular computer produces that coloring for 1834 cases, and
we attach all of them as one big appendix, and then it becomes like a 20,000 page paper. I mean, if that constitutes a formal proof, then fine. Okay. Now let's completely switch tacks and talk about some weird maps, like some really weird maps. Okay, all the rules we were talking about, there should not be bridges, there shouldn't be pieces, etc. They all go out of the picture right now. Okay, so here is a weird map. It has a strange name, which I'm not going to tell you about. Okay, so this map has 81 regions. Okay, and these regions are all arranged in a 9x9 square. Okay, and these 81 regions are all weird in the sense that all regions in a row and all regions in a column, apparently they're all neighboring each other. Like, they have bridges that are going all the way across. Maybe they have pieces in other places, etc. But they all say that, all of these regions have to be neighboring each other. Okay. Now, in addition, these 81 regions are broken up into zones of 9 regions each. There are like 3x3 squares. And they all say that everything within a zone is also adjacent to each other. Okay. And to make matters worse, some regions have already chosen their color. They say, no, I like red. I want my map to be colored red. I mean, whatever map you have, my color should be red. Okay. And now I ask you, can you color this map using 9 colors? Okay. What is this? This is Sudoku. That's just the Japanese kanji for Sudoku. As you can see, I mean, like this is just if you can think of Sudoku as just a different way of stating exactly the same thing. I want all rows and all columns to be numbered using 1 through 9, which is the same thing as saying we assign one of 9 colors to them. And what are the rules that you have? Everything in a same row, everything in a same column, and everything in a same zone, they must all get distinct colors. Okay, and we are asking, is there a way to fill the empty squares using numbers from 1 through 9 such that we are consistent with respect to all of them? Okay, Sudoku is just like a coloring in a very, very weird world. Yeah. Okay, good. So now I don't know if I should maybe turn the thing a little to the side. And this particular instance that is there is an example of what I would call a really, really hard Sudoku. Okay. And this puzzle was designed by someone called, this particular Sudoku was designed by a person called Arto Incala. And apparently, it is regarded as the hardest Sudoku that is present in the world. Okay. If you don't believe me, you can, I mean, the printout has the Sudoku in it on the other page. There's an easy one and there is a hard one. The hard one is the Arto Incala version. If you want, you can try it yourself. I would suggest that you don't try it here because it's very hard to make any progress in it. It was designed to be hard. Okay. Okay. But suppose I tell you that I know a solution to this. Okay. I have a solution. The solution is written here. Okay. I want to convince you that I know a solution, but I don't want to tell you the solution. I mean, I want to do it in a spoiler-free fashion. Okay. So I don't want to tell you that, what the solution is. I want to somehow reveal nothing to you. Okay. How do we even do something like this? How do I tell you that this Sudoku has a solution where at the end of it, you are going to be convinced, but you will know nothing more about it besides the fact that the Sudoku has a solution. Okay. So I'm going to try it out. I'm going to tell you exactly what I'm going to do. Okay. And then we will try this out as a demonstration. Unfortunately, because we have to keep putting it up again, I'm going to do this just once, but we'll try it out again. So here is what we are going to do. This is what is written. Behind each of these numbers is the actual answer that has been written there. Okay. Now, if I have made a mistake, either I have made a mistake in the sense that the rows are wrong. In the sense there is some row where two numbers have been used twice, like some number has been used twice or more. Or maybe the column is wrong, or maybe the zones are wrong. Okay, but I've already committed to an answer here. Now, here's what you can do. Let's say you don't believe me. So you can say, no, I want to check your rows. So what I'm going to do is I'm going to take each of the rows, neatly lay them down into 9 piles. I will shuffle each pile of them and give each pile to you. You can now check each pile and see if the numbers are 1 through 9 there. If I have made a mistake, you will catch me now. If I made mistake on the rows, you will catch me. Okay, so this way you can sort of say, okay, fine, you convinced me once, but I'm not satisfied. I want to do this more, because there's a 2/3 chance that I got lucky. Maybe I made a mistake on the column. You only check the rows. So we will repeat this experiment many times. And if I manage to convince, no, Sudokus, there is no diagonal constraint in this one. So this is what we are going to do. So I'll show you a like a small demonstration of what is going to happen, and then we'll try it out physically once here. Okay. So this is the sort of numbers that are present. By the way, I should mention that this particular protocol I'm talking about is a really cool protocol by Gradwal, Naur, Pincus, and Problem. Okay. So maybe I ask you, which ones do you want to check? What do you want to check? Do you want to check rows or columns or zones? I don't know. Oh, yeah, this should have been a 5. I forgot to put it there. Thank you. Yeah. So, okay. So maybe you say that, no, I want to check zones. So what am I going to do? I'm going to take each zone, put them into one pile, shuffle them all, and then say, please go and inspect them. Okay. And at this point, maybe you say, okay, fine, it checks out. I mean, like each of the zone seems to have numbers from 1 through 9, but you could have cheated. Maybe the mistake was in the row. So let's try this once more. Now what I will do, I will like painfully arrange all of these numbers once again on the board and then say, okay, now what do you want to check? Now you can say, now I want to check columns. Then we will take each of the columns, put them into 9 separate piles. And then you check that the columns look like 1 through 9. Okay. So we'll just repeat this experiment 10 times. And at the end of it, you will be 99% sure that I could not have cheated. I could not have gotten lucky 10 consecutive times in a row. Because every time you check me, there is a 2/3 chance, there's a 1/3 chance that you will catch me. And so the chance that I succeed all 10 times is going to be dropping a lot. Yeah. So, okay, either I make a mistake on the rows or the columns or the zones. You get to check one of them. If you catch the point where I made a mistake, you will catch me 1/3 of the time. But I could have gotten lucky 66% first time. So maybe you try twice. So I should have gotten lucky once. I should have gotten lucky the second time also. So it becomes 2/3 into 2/3. Maybe you're still not satisfied. You say, no, let me try once more. So it'll be 2/3 into 2/3 into 2/3. So you do that 10 times. Turns out that will turn out to be less than something like 1% or 2% or something. Yeah.
You could make 3 copies of it.
So for example, if we had a Xerox machine here, okay, you say, no, let's take this paper, let's make a Xerox of 3 different things. One of them I'm going to guess rows, one of them I'll check columns, the other one I'll check zones. That will convince you 100%. Okay, we don't have a Xerox machine. You could sort of say, hey, nice try. You would have put the rows correct here, columns correct in the next one, zones correct in the next one. So you need to put your trust somewhere. Okay. So now let's try it out in this. So I want people to just know, what do you want to check? Do you want to check rows or columns or zones? Okay. Everybody wants to check zones. Okay. So let's do this thing. Actually, can I ask someone to help? Okay, I'm going to shuffle all of this. Yeah. So I've shuffled all of them. You can check if it's all 1 through 9. Yeah, one zone at a time. Yeah, but don't look at the other side, huh? Okay, so here is somebody else wants to check. Was this all 1 through 9? Do you want to check this? Okay, you can pass it on to somebody else. Oops, something fell down. Yeah. Yeah. Okay. Do you want to check? Yeah. So as you can imagine, doing this 10 times in a row is going to take, a lot of arranging and taking it down, etc. So in fact, one of the things you can do if you want to try this at home is that take a piece of paper, write down the answer. If someone wants to check zones or rows or columns or something, cut the paper into rows or columns or zones, cut each of them into 9 individual pieces, shuffle all of them and say, please verify. Okay. So does someone else want to? Okay. Yeah, I know. So please don't ask me to do this again. So did it check out? Did it look like 1 through 9? Okay. So okay, good. So that is one way. This is one way to convince people that you know the solution to Sudoku without telling them what the solution is. And in fact, like before we even started this experiment, if I had asked you, what would you see in your pile? You all know that what you would have seen in the piles were numbers from 1 through 9 in some order. And what did you see in the piles? You saw numbers 1 through 9 in some order. So there is nothing that you learned more that you didn't already know. Okay, whatever you saw, you knew what you were going to see before anyway. You were hoping that it was something different so that you will say, haha, you cheated. Okay, but unfortunately there wasn't. Okay, and this is what is called a zero knowledge proof. Okay, a zero knowledge proof is a way in which I can tell you that something is true without telling you anything else about it. Okay, so this was first defined by Goldwasser, Micali, and Rakov, and it sort of revolutionized the field of cryptography in some sense. Like we owe almost all of modern crypto to many of the giants that are going to come up here. And after they defined the notion of zero knowledge, Goldreich, Micali, and Wigderson, who are the people in the column, they showed that anything that you can verify in a zero knowledge protocol. Okay, Sudoku was one example of it. Coloring is one example of it. Like if somebody gave you a coloring and asked you, is this a legitimate coloring? You can just check neighboring regions and figure out saying, okay, it looks fine. But coming up with a coloring seems to be difficult. Okay, and Goldreich, Micali, and Wigderson showed that anything that you can verify is verifiable in zero knowledge. Okay, and in their proof, map coloring is the central problem that they study. Everything centers around map coloring. Okay, and if you want to see more about the zero knowledge version of map coloring, there's a beautiful talk by Avi Wigderson on number file. It's called Zero Knowledge Proof, and I would highly recommend that people check it out. Something. So, okay. So that is with respect to, yeah, please go ahead. So, okay, I should have, if I remember right, it's like the late 80s or late 90s. Yeah, I think it was in the 90s. So the Goldwasser, Micali, Rakoff is in the 80s, and this one is in the 90s. Okay, so okay, this is all so far. Everything seemed to be fun. It's like coloring maps, solving Sudokus. They all feel like puzzles. Like what is the application in the real world? Okay, so here is how zero knowledge is used a lot these days. Okay, and let's say you are a person, you are talking to your bank. Okay, and you want to say, hey, I'm customer, blah, blah, blah. Okay, and then the bank says, yes, please tell me what your password is. Only then I will give you access to your account. And then you will say, oh, here is my super secure password. Okay, and at this point, you suddenly realize, oh, I'm not talking to the bank. I'm talking to Deadpool, somebody. Okay, I'm talking to somebody who I thought was the bank, but is somebody else. And now that somebody has my password. So this is a major risk. You don't want to do this. So what happens, many of the high security places these days, is that you say I'm customer so-and-so, and the bank then says, convince me that you know the password. Okay, it's like as if convince me that you know the solution to the Sudoku. And at this point, you do what is the zero knowledge protocol to convince the bank that you are a holder of the password. Okay, and you do it in a way which is spoiler free, so that if it was Deadpool on this side, Deadpool learns nothing. Okay, and this is something that is used a lot when it comes to verifiable voting. Many of the cryptocurrencies and blockchains that are currently available in the market. So Zcash is a rather popular cryptocurrency, and the Z in Zcash stands for zero knowledge. Okay, and many authentication mechanism where you want to tell somebody that I am so and so without giving them the password. You want to do this in some zero knowledge fashion. This is something that is used a lot.
But currently, the way we enter the password is not.
So there is a protocol that sort of mimics something similar in the sense that if someone was sitting on your ISP, they still can't figure out what is being sent. But the current way most transactions happen is not the zero knowledge, but many of these apparently high security places use such a zero knowledge situation. Like for example, this apparently gets used in the following situation also. Let's say you want to apply for a loan in a bank. The bank may say that you are eligible for this loan if your salary is between this and this. One way to tell the bank that you are eligible is by actually giving them saying, oh, by the way, here is my salary. But maybe you don't want to do that. Maybe you just want to tell the bank that, my salary is within this range without revealing anything else to them. Turns out there are protocols in some banks that actually let you do this, where you can show your eligibility to certain things without revealing too much private information. Okay. So this is how zero knowledge is used in the current world. OTP. So zero knowledge is more than that. I should know nothing more than the fact that you are the bank holder of 1, 2, 3, 4, 5, 6, 7, 8. Like for example, one of the ways in which I can tell you in the Sudoku thing, I could have just said, can I verify that these two numbers were different? I could have shown you these two numbers, but now at the end of it, you learn that, in the right solution, this was supposed to be a 7. Like I don't even want to tell you that. So the zero knowledge is truly zero knowledge. Like you learn nothing else besides the fact that the Sudoku had a solution. Yeah, please go ahead.
Example that you can show.
So the Sudoku example was an example of a zero knowledge.
Example like the solution. Like if I as a bank receive 1 to 9 numbers, it doesn't tell me whether.
Yeah. So the way it works is like, okay. Let me oversimplify this and say this was how Goldrake, Mikali, and Rakov. Goldrake, Mikali, Vigderson did the thing. So let me just show their faces so that I can talk about them. So they basically said that every person's account number is going to be one map, which is not colored. Okay, every person's account number is going to be one map. This map everybody knows. Different people have different maps. There's nothing private about it. But the password for your map is a coloring of this map using just 3 colors. Turns out your map can be colored using 3 colors, and that's your private password. Now you come to me and you tell me that, hey, I know a coloring of this map. And I will be like, I don't believe you. Show me that you know a coloring. There is a zero knowledge protocol for this. In fact, the zero knowledge protocol of Goldrake, Mikali, Vigderson was you put the colors of every region into locked boxes. And I can say, I want to check Ahmednagar and Pune. So you will open just those 2 boxes and show me that they will look 2 different colors. But every time you give me locked boxes, you shuffle up the coloring. Whatever used to be red, you call it blue. Whatever was blue, you call it yellow, etc. And the GMW protocol basically repeated this multiple times. So that's an oversimplification, but this is more or less what they do. Okay, that's how central coloring was in their proof. Okay, so okay, this is one reason why I should not have added animations that are like this, so that we can go to the next slide a little faster. Okay, so what did we see today? So let's just conclude. We saw that, how can you color maps using few colors, and how can you do that quickly? In some way in which you don't have to revisit a map, a region that has already been colored so far, etc. And you also saw how you can give a spoiler-free solution to a Sudoku puzzle. Okay, this is what we saw. But what I would like you to take away is like, what did you learn today? Okay, and the first thing I want to sort of say is that many of the things that we do may look simple and they may look like fun, they may look like puzzles, etc. But that shouldn't let you diminish you working about it or you thinking about this and something, because many of the times they have far-reaching applications. Yeah, there's a question.
I mean, the converse would be even better for the kids.
Yeah, like many times, often cool applications actually start off as nice puzzles. You're trying to just solve puzzles, and you start wondering about, can I do it with 4 colors? Can I do it with 3 colors, etc. And that will lead you to wonderful applications in the future. Okay, that. And second thing I want to sort of say is that mistakes are not a bad thing. Okay, like for example, Kemp's proof was wrong. It took 11 years to find out that the proof was wrong. But the point was, people still learned something out of it. They learned from the fact that, okay, it may be wrong, but we now know that the 5-color theorem is true. And much of the later Appel and Haken proof also, it built on top of Kemp's ideas and so on. And similarly, in zero knowledge also, we were sort of saying that I can convince you 99% of the time if we didn't have a Xerox machine. And the fact that it is 99% and not 100% gives you a lot of power. So something that, like making errors is not a bad thing. Like the thing that you should take away from it is that as long as you learn something new at the end of it, that's what matters. Okay. And that's all I wanted to say. So let's go have chai. Yeah.
I have a thought to this.
Yeah.
Maybe one more way to this would be that instead of trying to validate that I'm right, let's try and prove that I'm wrong. Would that be a way to also see the whole Sudoku?
So that's also one, because these things look like you're trying to catch me making a mistake in some sense. Yeah, that's a different perspective also that we could take.
Okay.
Yeah.
Thanks. I think. So this is just for the online audience. Thank you for joining us. We will, of course, online audience, you don't get chai. We will have some more discussion here, but we'll end the live stream in a bit. Just to tell you that 2 weeks from now at Ruparel College, we're going to have Nishita Kulkarni, who is a theoretical physicist, take a session. And we'll be back here in a month for chai. So be with us, and audience here, we can go down, have chai, take a break, and come back and ask him a lot more questions. Maybe we can try and do Sudoku puzzles or something. But, you can end the live stream then. Thanks. Okay, so have chai. You have to tell us something more of the Sudoku, because I don't even know how to start on the.
Yeah.
The left one is easy.
I know. I know.
But don't spoil it.